build an insecure system out of perfectly good cryptography. And it's sort of a good talk for researchers who are worried about like the provable security aspects of the actual cryptographic things. And what I'm saying is that there's a whole bunch of system issues that people get wrong, even if the cryptography is good. So there's so many other areas of security. So there's a whole bunch of different examples that I give. So I can skip over depending on whether you guys look bored or whether I'm running out of time or whatever. So the first thing is proofs. It's hard to get any sort of security paper published without a formal proof of security. And if something comes with a proof of security, you'll feel safe using it, even if you don't understand the proof. So, but proofs are neither necessary nor sufficient. So, I mean, you know, in a lot of cases it helps, but, you know, don't just rely on that. So here's an example of a provably secure cryptographic system. It's really the only provably secure cryptographic thing, which is exclusive OR with a one-time random number. Because no matter how much compute power you have, you can't tell what the plaintext might have been. So just to review XOR, if you XOR with the same thing twice, you sort of undo it. So A, exclusive word with B, exclusive word with the same thing B again, you'll get A. And doing it in any order, you know, you'll have the same thing. So let's use provably secure cryptography to build a system which is a keyless way to send a secret. So the idea is that Alice wants to send Bob a secret, a message, but they don't have a shared secret to do it. So the physical mail analogy, I have a nice picture here, is Alice puts the secret thing in a box and locks it with a really good lock. Sends it, mails it to Bob. Bob can't read it because he doesn't have, the key to Alice's lock, but he puts his own lock on it, sends it back to Alice, and can you see the, and then Alice removes her lock, sends it to Bob, and he can remove his own lock. And at all times, it's been protected in the mail system. So we can do the same thing with keyless cryptography, which Alice chooses her secret, A, Bob chooses his secret, B, and she locks the message by XORing it with A, so it now has Alice's lock on it, and now Bob adds his own lock by exclusive ORing with B, sends that to Alice. Now Alice can remove her lock by exclusive ORing with A again, sends it back, whoops, and it's now, she gets rid of her own lock, and it's now exclusive ORed with B, and Bob can read the message by exclusive ORing with his thing, which is like incredibly cool, and you're using provably secure cryptography, but it's not actually secure because if you exclusive OR the 3 messages on the wire, you get the message. So anyway, another proof story is that one of my earliest papers was analyzing the first example of a link state protocol, which was the ARPANET algorithm. And I noticed that it wasn't stable, that if you just injected 3 bad messages, the network would be down forever. Now that's like really bad. We're used to that all the time with PCs and so forth. It gets into weird states, you just reboot it. How do you reboot the internet? So the internet has to be like a whole lot more robust than that. And actually, the ARPANET, after I published the paper, it actually got into that state where there was kind of a sick router generating random messages. And, right? So that was kind of really cool. But one time somebody, there was this fad of proof of protocol correctness systems. And all the papers I found, really boring. It just wasn't kind of my thing. And they had this toy thing that they would always prove correct with it. So one time somebody said to me, "Oh, Radia, you do protocols, and I have a great protocol proof of correctness thing." you should look at it. And I was trying to be polite and acting interested when I wasn't. And I said, well, have you proven anything real with it, or just this toy thing? And he said, oh, I proved that the ARPANET thing was correct. And I said, but it's not correct. And he said, yes, it is. I proved it was correct. And I said, but if you inject 3 bad messages into the network, it will be down forever. And he said, well, if you inject bad data, what do you expect? So what is the definition of correct, and so forth? So anyway, so next topic is authentication handshakes. So cryptography allows you to prove that you know a secret without divulging the secret, as opposed to like sending a password where whoever you've just told the thing to now knows your password. So there's 2 types. There's a secret key or symmetric key, where Alice and Bob share the same secret. And then there's public key, where each side has 2 keys, which are inverses of each other. Everyone knows one of the keys, and they keep the other one secret. So with secret keys, Alice and Bob both know the same secret S. With public keys, Alice has a pair of keys, her public key and her private key. Bob has a public key and a private key. Everybody knows everybody's public key, but only Alice knows her private key. So a bit of notation. These curly brackets with K on the end means message is encrypted with key K. And square brackets with Bob means this message is signed with Bob's private key. So an example of a secret key handshake. Alice and Bob both know a secret K. So Alice wants to prove she's Alice. So she sends a message saying, I'm Alice. Bob chooses a random number and says, oh yeah, if you're Alice, prove that you know the secret by doing some math with it. And so Alice encrypts the challenge R1 with the key K, and Bob can verify that's what that she must know the secret. But it's easy to get things wrong. So let's say that not only does Bob need to know that it's Alice, but Alice needs to know that it's Bob. So we're going to do mutual authentication using the shared key K, where Alice proves to Bob and Bob proves to Alice. So Alice says, I'm Alice. Bob sends a challenge, R1, and then Alice sends the answer to that challenge, R1 encrypted with K. And then Bob sends, then Alice sends a challenge to Bob, which is R2, and Bob encrypts it, sends the answer to Alice, R2 encrypted with K. So there's nothing wrong with this protocol, but if you have any soul as a protocol designer, you'll realize you could have done it in fewer messages. So let's fix this up to be fewer messages. So Alice says, I'm Alice, and puts her challenge in that same message. And Bob sends his own challenge, R1, sends the answer to Alice's challenge, and then Alice sends the answer to Bob's challenge. Okay, well, there's this thing called the reflection attack, which is Trudy, who's claiming to be Alice but doesn't know the secret, says, I'm Alice, my challenge is R2. Bob sends the answer to R2, and his own challenge, R1. Now Trudy is stuck. She doesn't know how to encrypt R1, but that's not a problem. She opens a second connection and says, I'm Alice, my challenge is R1. And Bob helpfully gives her the answer and gives another challenge, but now she can complete the first one. And so you're talking to a computer. The computer doesn't know any difference. So, yeah. Anyway, so that's a whole thing, is designing cryptographic handshakes, and it's very easy to get them wrong. Now with public key cryptography, Alice tells everybody her public key and keeps her private key secret. And so the public key and the private key are sort of mathematical inverses. It's sort of like as if nobody ever invented division. They only know how to do multiplication. So your pair of keys can be 5 and 1/5, which are inverses. So if somebody wants to encrypt a message for you, they multiply by 5, and if you want to undo it, you use the private key, which is 1/5. So this sounds really cool, but how can I tell everybody 5 and they can't figure out the inverse 1/5? And I say, oh, well, the math is like all special where you can't do that. And then you're happy for about 4 seconds, and then you go, excuse me, if it's impossible to figure out 1/5 given 5, how did Alice come up with these 2 numbers? And that's a whole really cool thing, but not terribly relevant to this lecture. So anyway, with public key authentication, Alice's key pair is her private key and her public key. So Bob knows her public key, Alice knows her private key. She says, I'm Alice. Bob picks a random number R as the challenge, and let's say he encrypts it using her public key, and says, oh yeah, if you're Alice, tell me what number I was thinking of. And she reverses the encryption with the public key by operating with her private key and sends back R. So, well, there's nothing exactly wrong with this, except it's extremely dangerous to operate on things with your private key. Because how do you know what Bob actually sent to you? It could be that the challenge was the digest of a message that she's now given him the signature on. Or it could be the header of a message that the way you encrypt with a public key is you encrypt with a secret key, and then in the header you put the secret key encrypted with the public key. And so we could have sent her the header of that thing, which she applies her private key to, and is now telling Bob the decryption key for this message. So, you know, again, designing handshakes is a whole cool thing. But let's look at other issues. So setting up keys. So with secret keys, you need a different secret for each pair of users. How do you do all that configuration? You know, on the internet, can you imagine needing to configure a different secret in there? And with public keys, even though it seems easier, you just tell everybody what your public key is, unless there's a very secure mapping between Alice and the public key, somebody can impersonate her if they can convince you that a public key, a different public key that they know the private key to, is Alice. So we use introduction services, or known as trusted third parties. So with secret keys, you could configure n² different keys. You configure into everything a secret to share with each of the n-1 other things, but that would be very painful. So instead they use something called a key distribution center, where everybody knows one secret, which is the secret they share with the KDC. And the KDC knows everybody's secret. And if Alice wants to talk to Bob, the KDC securely creates a new random number and sends it to Alice using the secret it shares with Alice, and it sends it to Bob saying, Alice, if you want to talk to Bob, use K sub AB, and Bob, if you want to talk to Alice, use K sub AB. So now Alice and Bob can talk to each other. And various deployed systems, there's Kerberos, and then there's Microsoft's Active Directory, work this way. Now, in contrast, let's look at if you're basing it on public keys. So that's like the PKI and certificates and all that. So the idea is that there's this trusted thing known as a CA that signs a message known as a certificate that says, Radia's public key is this number. And so if everybody knows their own public-private key pair, and they have a certificate signed by the CA saying Alice's public key is this, and everyone knows the CA's public key, everyone can authenticate. So communication using certs, Alice says, here's my certificate. And since Bob believes the CA, he can look at the signature of the CA on this thing, and now he knows Alice's public key. Bob sends his certificate, and now Alice and Bob can talk securely. Now, the way that it should work, even though kind of the deployed things don't work this way, the CA should not be on the network. There's no excuse for it needing to be on the network. So if you imagine you get hired, you get a badge, and at that point someone drags the CA out of the vault and signed your public key. Then it should write your certificate on some medium, like a USB stick, and you carry it to their directory, and the directory should be displaying all of these certificates, so it's easy to look up. Now, with revocation, yeah, that's another whole thing. You probably want something online that will tell you what certificates have been revoked, but it's not going to be as security sensitive as putting the actual CA online. And it's sort of like the way stolen credit cards are dealt with today. It used to be they would publish this book that had all the bad ones, and that was very expensive to have to publish this physical book. Now, every time you try to use your credit card, they have to make a call to some central thing that looks to see if your credit card has been stolen. So when you use HTTPS, you say, hello, website, and the website says, here's my certificate, and now you know the public key and you can talk securely. Now, let's look at the functional differences between doing it based on a Kerberos style or a public key style. The KDC solution is going to be less secure because it's a box that must be online, which means that if there's any sort of security vulnerabilities, it can be attacked across the web. It has to be replicated for performance and availability, meaning any one of the replicas could be broken into. And it's physically broken into. And it's a complex system, it's likely to have exploitable bugs, and it has a highly sensitive database of all user secrets. Whereas the CA, the public key-based thing, is offline. It never knows any user private keys. And it's basically a glorified calculator. There's what would it mean to have a security flaw or something? So the cost, the KDC solution is going to be much more complicated because it has to be fast, and it has to be talking across the net. And it has to always be up, because if it's ever down, no one can do anything, so it has to be replicated. Whereas the CA, again, can be a simple thing, and if it takes a few days to fix it, it doesn't really matter. And performance, a third party, when Alice can talk directly to Bob without having to first talk to the KDC, so it will be faster. Now also for privacy, the KDC knows everything you talk to. Every time you try to talk to anything, you have to talk to the KDC first, so it knows everything that anybody talks to. So the KDC is an availability issue, a performance issue, a security issue, and a privacy issue. Now, there's another thing that they're using on the web. I call them bearer tokens, which looks like they are using public keys, but it turns out not to have any advantages over a KDC system. So Alice says to the authentication service, and this is what happens when you go to a website and it says authenticate with Facebook. Facebook is acting as this authentication service. So you say, I am Alice, I want to talk to Bob, and the authentication service can authenticate you with username and password or anything that it wants. And then it signs a message saying, whoever has this message is Alice. I've authenticated her. So it's signed by the authentication service, but you don't have to prove, like with the KDC, you have to prove you know the secret in order to actually talk to Bob. This message from the KDC is not enough. You have to also know the secret. Here you don't need to know the secret, just if you have this thing. So if Alice were to be fooled into talking to something that wasn't Bob, then and got this token signed by the CA saying the holder of this thing is Alice, then this fake Bob could impersonate Alice as the real Bob. So this system is no better than a KDC, even though it's based on public keys. It has the same problems of availability. If it's ever down, no one can do anything. Performance, because you have to talk to this extra thing. Security, because it's an online thing that can impersonate anybody. And privacy, it knows everything that anyone talks to. So I'm sort of sad that the world seems to be going this way rather than with kind of the straight public key stuff. Okay, so a new topic. When you're using the web, you're using a protocol called HTTP. And it's stateless, meaning that the server doesn't remember anything about you. You just talk to it with simple commands like get, and you say, get this thingy, and it will respond with the thingy, or post this thing, and it will store that. But when you're actually using the web, you get the impression that you've logged onto something like Amazon, and you're doing a whole shopping cart, and it seems to know all this stuff about you, and it seems to remember. How does it do that? Because it's just this simple request response. Amazon doesn't remember anything more after that. So the way to create the illusion of a long-lived session is, again, your experience is it's a long-lived session somehow. So this is done with this thing called cookies. Now, what is a cookie? It's a little file that the server sends to your browser. So when you, and your browser has this little file in some obscure place that says, these are all your cookies. So it'll say, this is the Amazon.com cookie. This is the bankofamerica.com cookie. And it doesn't try to read it or it doesn't understand it at all. It just stores it there. And then whenever you talk to Amazon, you look in this file, and if you have any cookies there that were sent to you by Amazon, you'll send that same thing back. So that's kind of the standard, just tells you the browser exactly what to do with it, which is that in the message there's a place for Amazon to send a cookie, and when you send something, you send any cookies that have the name of the thing you're talking to Amazon. So Alice has this little directory for cookies, and when she talks to Amazon, she'll send the whatever little bits that Amazon have told her to send. So the standard didn't say how you're supposed to use this. Now, what they had in mind was that you might authenticate, and then Amazon would say, yeah, this is Radia. So they knew that it would be a problem if someone could steal that cookie, because then they could claim to be Radia. So they do talk, this communication is done with SSL. So an eavesdropper can't steal these cookies. But what they, so for eavesdroppers, you use SSL, which means that the conversation is encrypted and an eavesdropper can't steal the cookie. And yeah, there's the issue of the bearer token talking to the wrong guy, and you hope that the SSL's protocol with certificates prevents that. But what they didn't think of was that the user themselves might be malicious. It just didn't occur to them. Now, what could the user do that was malicious? Well, a very prevalent form of using cookies was as your shopping cart. So it would say the items you were buying and the price, and it was not encrypted to the user. It was encrypted over the wire, but in the user's own machine, there was this plain text thing that said, the Amazon.com, this is the Amazon.com cookie, and you're buying item number whatever for $92.16, and you're buying this other thing. And so enterprising people who figured out where the cookie files were noticed this and could change the prices on things. And so, I know of someone that was trying to tell AlaskaAir.com that he could buy a ticket for whatever price, and the person was saying, yes, isn't it great? You can sort of decide on whether it's first class or whatever. And he was saying, no, you don't understand. And so he said, let me show you. So he bought a first class ticket to someplace for like $1. And the person said, oh my, that's probably not right. So, they appreciated the fact that so they let him fly on the $1 first class ticket, and they fixed the bug. But there were a lot of merchants that did this same thing. So, anyway, there's lots of other misuses of cookies in one of my favorite papers called The Do's and Don'ts of Client Authentication on the Web, if you want to read that. Now, standards. This is another topic. Things are so incredibly confusing. There's always like 3 things that sound like they're solving the same problem by different committees. I always want to understand the difference between technology A and B, and nobody does that. So either, you know, the best you can do is they'll hand you 2 different 600-page specs, all with their own jargon, you know, for no good reason. And, you know, it gives you a real headache. People might be experts on A or B, but nobody thinks about comparing them. So if I ask an expert on A, how does it compare with B, they'll say, A is awesome and B sucks. And you ask the B person, you get the opposite answer. And then sometimes, you know, this has happened where after studying it, I realize some things about B that are better. And I tell the A people, actually, B has these features, and it works better in this case because whatever. No problem. The A people steal the ideas, and nobody actually cares what's inside their spec. They just want to get credit for it. So both A and B are moving targets, and this is just incredibly frustrating. So the way that I tell people is it's natural to think of standards bodies as well-educated technologists that are carefully weighing engineering trade-offs. But a much more accurate way to think of them is as drunken sports fans. So it's like, rah, rah, my team. So, but here's an example where instead of inventing something new, a standards body adopted a syntax invented by a different standards body, which sort of never happens. So this is wonderful, and I would ordinarily applaud them, but in this case it was like really a bad idea, and I'll explain why. So, a standards body, which was the IETF, which does the internet things, adopted a format for a certificate which was done by ISO, a different sports team. So a certificate, what is it? It just matches a name to a public key. So it's a little message that says the name Radia goes with the public key, whatever, signed by the CA. It's so simple. How can that possibly matter? And so the IETF PKIX group, and these are the format of certificates you use when you're using SSL on the web, they decided to base certificates on X509. I'm sorry, it's ITU instead of. So why should it matter? So the problem with X509 is that it maps an X500 name to a public key. Now what's an X500 name? It's a perfectly reasonable hierarchical namespace where you're used to names of the form Amazon.com. But this namespace, which is also perfectly reasonable, where they have these different components, and instead of just having periods between, they actually say what type of thing that component is. So one of the components is C equals, which means what country it is. And so the first component is always C equals something, which is the country. O equals some organization name. OU would be an organization unit name, whatever that is. You can have as many of those in this hierarchical namespace that you want. And the very bottom thing is called the CN, the common name, just kind of a whatever nickname you want to put in there. So, for instance, you can say C equals Canada, O equals UBC, OU equals computer science, and CN equals the best major. So that would be an X500 name. I may have used the wrong example. I don't know. So X509 would have been a fine choice for certificates if internet protocols and internet users were using X500 names, but they weren't. And they don't. They use DNS names that look like something like labs.examplecompany.name.com. I'm not supposed to use real names in these slides. So anyway, so what good is something that maps a string that the application and user is unfamiliar with to a public key? So an example is the human types foo.com, which is some DNS name embedded in a URL, and the site sends a certificate with an X500 name, like C equals US, O equals Attica prison, OU equals death row, OU equals particularly vile prisoners, CN equals horrible person. So one strategy by some implementations, especially early on, was to ignore the name in the certificate because they knew it would not match the string in the URL, so they didn't worry about the name at all. But they did check the validity of the CA signature. So what security are you getting? You're getting zero security if it's not looking at the name, but if it can't match the name because it's a different string. So the only security that gives you is the warm, fuzzy feeling that somebody paid somebody for a certificate. So they've kind of fixed that by having at least 3 different ways of embedding a DNS name into the X500 name. So one thing was to invent a new category. Instead of C equals, which is like country equals, they invented a new thing for DC equals, domain component. So you would make labs.emc.com would be DC equals com, DC equals EMC, DC equals labs in order to translate the name. Or there's a field in the PKIC certificate where you can say alternate name. You can put it in there. Or you can use the bottom of the X500 hierarchical name, which was the common name, and put the DNS name there. Now, are 3 ways better than 1? No, because if the CA enforces that when you request a certificate that you own the alternate name, but they ignore what's in the common name and lets you put anything in there, and someone's browser is looking at the common name, again, there's sort of no security at all. Now, another problem is just playing with human names. So I'd love humans to be authenticated with certificates and keys, but what do we do for names? So if all parents were as creative as mine, there wouldn't really be a problem. I am the only Radia Perlman on Earth. But if you work at a big company and you want to send email to John Smith, you have to figure out whether it's John Smith or Johnny.Smith or John.Q.Smith. So the way I would solve this problem is if I were a hiring manager and someone came in, I'd say, wow, your resume is spectacular and we need someone just like you, but we already have a John Smith, so we can't hire you. We'll start getting more creative. And even if you solve the name problem, all the math in the world will not help you know who or what to actually trust. So imposters have just walked into hospitals dressed as doctors and performed surgeries, or even had the proper credentials, like Bernie Madoff had impeccable credentials. And we don't tend to search for things with DNS names anyway. So, there's a lot of this math, but the whole foundation is quicksand. Yeah. So we search for things by your kid eats some rat poison. You quickly search on the internet antidote for rat poison and something comes up. How do you know to trust that information? It's right. So, okay, so the next topic I'll talk about, I'm running low on time, I think, this is one I'm really passionate about, so let's see if I can get through it. Trust models for PKI. So, what is PKI? It's a way for me to know your public key. And I've given sort of cutesy names to all of these different models, and I'll explain what each one is. So, who exactly is the CA? So one model is the monopoly model. Let's choose one organization universally trusted by all organizations, countries, etc. Embed their public key in absolutely everything. Everyone has to get certificates from them. This is very simple to understand and deploy. But there is no such thing as a universally trusted organization. Also, if you ever did allow one organization to be that thing, they'll gradually raise the prices because it'll be so hard to convert to any other public key. And that one organization can impersonate everybody. So the next one is what's in your browsers, where it comes configured with 100 or so trusted CA public keys. It's actually like 300 these days. Usually you can add or delete from that set, and it does eliminate monopoly pricing, but it's less secure, because before you had to find one employee that could be bribed or tricked or whatever at the one organization. Here you have 300 organizations, and if you can find a weak link in any one of these organizations, you can get a certificate to impersonate anything you want. And you know, even if all of them were trustworthy, who checked out these organizations and how did they check them out? And in general, the answer is not good. It's basically you pay the browser vendor to put your public key in there. And also, if you were, this is a typical thing that happens, where you try to talk to something and you get this obscure pop-up box that says, this CA root certificate is not trusted. To enable trust, install this certificate in the Trusted Root Certifications store, and you click Install Certificate. Now, how is a human supposed to know what this is about? So it sounds good, you know, click on it, and now you have a new trusted thing in your thing. Okay, so the next, you know, thing that allows more flexibility is to allow a configured CA to issue certs for other public keys. So that instead of, when Alice tries to talk to Bob, instead of Bob needing to have a certificate directly in Alice's certificate store, Alice can present a certificate from something in Bob's store that points to a different CA, and that CA can issue. So Bob, if Alice, I did it the other way. If Alice is configured to trust X1, Bob can have a chain that says X1 says this is X2's key, X2 says this is X3's key, and X3 says this is Bob's key. So now I'll talk about the anarchy model, which is like the PGP web of trust, which is nobody tells you who to trust. You've met some people, they seem trustworthy, they give you their public key on a business card, you configure it in your machine, and every time you have a gathering of nerds, you have a PGP key signing party with some sort of ritual. And you have these public databases of certificates that anyone can donate their certificates to. And also when I want to find Bob's public key, if I don't have it configured, I try to find a path from one of the keys in my own machine through the certificate chain in the public thing to get to his name. So the problem is this is not going to scale. You can demonstrate, see it works when you have a small community of all trustworthy people. But if you tried to do this for the entire internet, just, you know, the sheer size of it, 1 billion users, each one with, you know, signing 10 things, and there's no practical way to tell if the path can be trusted. Just because mathematically a path works doesn't mean it can be trusted. So more or less anyone can impersonate anything. So now I'll talk about how I think it should work. So instead of believing that a CA is trustworthy or not, it's not like a binary thing. Instead, it should be trusted for a portion of the namespace. So the name by which I know, or you know me, implies who you trust to certify my key. So if you know me as radia.perlman.emc.com, you would trust emc.com to certify that name. If you know me as roadrunner279.socialnetwork.com, you'd trust socialnetwork.com to certify the key, or credit card number, whatever, at Big Bank. Whether these are the same carbon-based life form is irrelevant. So in order to do that, we need a hierarchical namespace, and we have it. It's called DNS, where each node in the namespace represents a CA. So people naturally think of what I call the top-down model, where you're configured with the root key, and in order to get to somebody's key, you just follow the namespace down. But now we have the same problem of a monopoly at the root, you know, both for pricing and also it can impersonate anybody. So now we're going to make a subtle change to this, which is each ARC in the namespace will not only have a certificate where the parent signs for the child, but also one where the child signs for the parent. And then you don't have to start at the root. You can start anywhere, including your own key, and navigate any place else in the hierarchy. Now, another thing is what I call a cross certificate, where any node in the namespace can certify any other node. Now, why is that? Well, one is so that you don't have to wait for the whole PKI of the whole world to be interconnected. You can have a little PKI in this organization, a little PKI there. You cross-certify, and then anyone in this namespace can find keys for the other namespace. Also, you can bypass the hierarchy for extra security. So here's where two different organizations have their own little PKI, and they can cross-certify and they can get to each other's names without waiting for the whole PKI to be connected. Or if you don't trust the root, you could directly create a link to this thing, and then everyone in this namespace won't go up that way. They'll instead take the cross-link and get to these guys. And even if all of this are malicious, it won't matter. So you start somewhere, wherever you're configured to start, which might be the root of your organization, or it might be your own key. And if you're at an ancestor of the target name, you just follow down. Otherwise, you look for a cross-link that gets you to an ancestor, and then you go down. And otherwise, you go up a level. So this sounds like I've recreated the anarchy model, but no, because you don't explore HP.com in case they know how to get it to IBM.com. You just, you know, follow these rules, which is you either go up one level or you follow a cross-link, and once you follow a cross-link, you'll go down. So the advantages of this model is that security, what's presumably most security sensitive to you, which is authentication between resources in your own organization, the trust paths do not leave CAs that are managed by your own organization. So all of the other CAs in the world can be arbitrarily malicious, but it can't affect authentication within your own organization. There's also sort of no single compromised key that requires massive reconfiguration, that even if there was some global PKI and there was some root that had to change its key, it wouldn't affect me as a user. I don't have to change my own key, I don't have to change my own certificate. Somebody way up in the hierarchy does all the magic about revocation and whatever for that one stuff up there, but it doesn't affect me. So malicious CAs can be bypassed and damage contained. So with the summary of this part is cryptographic algorithms and certificate format leave out the hard decisions of the trust models. The world doesn't seem to understand, you know, what I just said, and it seems so obvious to me. So my co-author actually was in the DNS, was active in DNS security, and got them to put in the crosslinks and the uplinks. And then he stopped going to the meetings, and people said, wait a minute, we don't need to have crosslinks or uplinks. We just need the Dell link. So the DNSSEC is a top-down hierarchical thing. So anyway, okay, so this one I'm going to skip. So now I'm going to go to humans. Stupid user interfaces, and do not parse this wrong. I do not mean stupid users. I mean stupid interfaces. So there's all these things that train users to type their username and password. So I constantly get pop-ups from who knows what, usually Outlook, that asks me to type my username and password. any sort of process can put up that box. And it's not happening as a result of something I did. It's because some server went down. And my Outlook, which is always trying to keep my mail up to date, when the server comes up, it says, oh, you have to re-authenticate, type your username and password. And I do, even though I know it's a completely insecure thing to do, but I want to get my email. So, right. Any malicious application can put up that box, and pretty much any user, certainly including me, will type their username and password at that point. Another example is abetting social engineering criminals. So there are these, diseased vermin, and I don't mean to insult diseased vermin, but they call you up. I get like a call every week saying, I'm from Microsoft IT, and your machine is, is broken, has malware on it, and I will fix it for you. So I was actually sort of curious where this conversation would go. I knew this was a criminal. First I said, well, how do I know you're from Microsoft IT? Can you give me a phone number to call you? And he said, certainly. So I called the phone number, and he answers and says, Microsoft IT. I get these calls so often, I can play with them lots of ways. One time I said, which machine? He says, oh, your machine, people are complaining because it's compromised. And so I say, oh, which machine? I have a lot of them. And he goes, all of them. So anyway, so then I said, okay, how do you know it's compromised? And so he shows me how to open this thing that I did not know was on my machine. It's called the event viewer. I have no idea what it's for, but it logs all these kind of scary things. So, which users don't need to know about. None of these things matter. But he shows me this, and boy, it looks scary. He says, look at all these red errors and these warnings. This is really bad. I will fix it for you. And so he said, okay, so now install this thing or do this command to let me have control of your machine. At which point I said, oh no, look at the time. I have to go pick up my child at the daycare center. And he said, oh, well, this is important. And I said, my child is important too. He said, this is more important. So, I hung up on him, but yeah. So, the problem is that this perfectly harmless thing could certainly scare users, right? Okay, so it's common when you're designing something to have to trade off usability versus security. So you would expect some sort of graph like this. The more usable it is, the less secure. The more secure it is, the less usable it is. Well, the industry has managed to find this spot, which is minimally secure and minimally usable. So, for instance, user authentication. Every site has different rules for usernames and passwords. It has to be at least n characters or no more than X. It must have at least one letter, one number, or it must not contain anything but letters and numbers. This was a great thing I saw on the internet once. Sorry, but your password must contain an uppercase letter, a number, a haiku, a gang sign, a hieroglyph, and the blood of a virgin. So they make it even worse. If you can't remember your password, they won't tell you what the rules were. If they did, at that point, you might be able to reconstruct. But then, if the user goes through all of this annoying stuff for changing the password, after they're sure that it's you and they're allowing you to create a new password, they won't allow you to use the one that would have been perfectly secure to keep using if you'd remembered it. Why are they punishing you at this point? There's these security questions, and this was something that I actually came up with, that I actually encountered. Father's middle name. My father didn't have a middle name. Second grade teacher's name. I couldn't remember my second grade teacher's name when I was in second grade. Veterinarian's name, I don't have a pet. Favorite sports team, what's a sport? And then my middle name, well luckily I do have a middle name, it's Joy. So I typed in J-O-Y and it said, not enough letters. So, you know, there's annoying rules that add nothing to security. You must change your password at least every N days. You can't reset a forgotten password to a previous ones. These sorts of rules actually lower security. And I asked a friend in IT, why do you do this? Do you enjoy torturing users? And he said, yes, we certainly do. That's the best part of our job, but that's not why we do it. The problem is, if we ever get broken into, I mean, you know, there are these best practices documents. If we ever get broken into, we can defend ourselves by saying we followed everything in that to the letter. Whereas if we said we knew that this stuff was, you know, lowered security, so we ignored that, it's, you know, you're much more vulnerable to, you know, legal things. So, user authentication. I do not want to hear people saying we need better user training. That's not the problem. So, or things like people shouldn't click on suspicious links. You know, what's a link and what's a suspicious link? So this is a quote that I actually wrote in the book, and after I wrote it, I said yes, and I think everybody should take this to heart. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It is astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our protocols around their limitations. So that's it. Thank you.